To understand this limit of a function, let's consider this example first. Let's discuss on how come the limit of 4x minus 5 as x approaches 2 is equal to 3. Let's consider this graph of 4x minus 5 with the interval -1 to +4. For the benefit of others, let's have some labels based on the definition. Here, 4x minus 5 is the f of x, or the function. L would be the limit, which is 3, and 2 would be the letter a. Now we are ready to prove that the limit of 4x minus 5 as x approaches 2 will really be 3 based on the definition of a limit of a function. And so let's consider this part of the definition that says given epsilon greater than 0, however small, there exists a delta greater than 0 such that this would happen. So yes, let's now prove that the limit of 4x minus 5 as x approaches 2 would be 3. Our assumption here is the existence of epsilon greater than 0. Now when we have to show that the limit is 3 for this function, it also means that we just have to find a delta greater than 0 such that this happens. One way to prove the limit of a function is to work backwards. In here, 4x minus 5 minus 3 is the same thing as 4x minus 8. If you want to be reviewed in operation of integers, just click the suggested video there at the upper right corner of your screen. Notice that we can factor out 4 here, so we have 4 times x minus 2, which is less than epsilon. And this is the same thing as 4 times the absolute value of x minus 2 less than epsilon. That gives us the absolute value of x minus 2 less than epsilon over 4, because we divide both sides of the inequality by 4. Notice that by definition, the absolute value of x minus 2 is indeed greater than 0. And now this part right here is the same thing as this, which implies that delta that we would be picking up would be epsilon over 4. As mentioned earlier, we just have to find a delta greater than 0, right? Notice here that we found a candidate for our delta. How sure are we that our delta here is positive or greater than 0? Note that epsilon is greater than 0, that's positive, and our 4 here is also positive, so positive divided by positive is still positive, and so our delta here is a positive number. And for the verification of the choice of delta that we have here, which is epsilon over 4, this happens. See, working backwards here is effective. The choice for the delta that we got, which is epsilon over 4, satisfies the definition of a limit. Now let's try to illustrate this proof and this definition of a limit of a function to know the use of this delta and epsilon that we have. Let's have an increment of 1 for x's here, and let's start with 10 until 2 since we are considering here as x approaches 2. And let us see if the y value would be towards 3 as well. So f of 10 this time would be substituting 10 to x in 4x minus 5, so that would give us 4 times 10 equals 40 minus 5, and so that's 35. Similarly, f of 9 would be 31, f of 8 becomes 27, and f of 7 becomes 23. As noted, the increment for x's here is 1, but notice that the increment for y's here is 4. So every time we move one step in x's, that corresponds by 4s in y's. Epsilon would actually be the distance between our y values here, or the increment that we had, and delta would be the distance between the x values. And notice in the proof that the delta would actually be epsilon over 4. And that is really true in this example. See, our epsilon here is 4 divided by 4, and that is 1. And since delta is equal to epsilon over 4, that gives us indeed 1. Let's have this time the other way around. Say we know the values for y, and let's have 200 as our starting point with an increment of 100. Definitely we can now solve for delta. Since delta is equal to epsilon over 4 and epsilon is 100, delta would be 100 divided by 4, which is 25. Let's now solve this algebraically. Since y is equal to 100 and y is equal to f of x, that becomes 200 equals 4x minus 5. Transposing negative 5, that would be 205 equals 4x. Dividing both sides by 4, that gives us x equals 51.25. And since the increment here for our x's would be 25, f of 300 becomes 76.25. Adding 25 to this gives us f of 400, which is 101.25. Let's verify if our x's here are correct. F of 51.25 would be 4 times 51.25. Whatever the answer is, we are to subtract 5. And indeed, the answer is 200. Similarly, if x is equal to 76.25, substituting that to the function f of x, that is 4x minus 5, y would be 300. Lastly, if x is equal to 101.25, indeed, y is equal to 400. You see, this is what it meant with the phrase however small for epsilon in the definition. To the point that if our epsilon here would be 0.001, that is, if our y here starts with 2.005, with the increment of 0.001, the next would be 2.004, and so on, we'd still be able to find a delta greater than 0. For the benefit of others, let's have this. It says that the limit will be 3 as x approaches 2. So let's see both sides of these numbers. What could the increments be with the solved delta that we had earlier? Here, epsilon, or the increment for the y values, is equal to 1. So how much is delta? Delta would be epsilon over 4, so that would be 0.25. Of course, one way of checking if these values are correct is to plot this on the graph. These values are indeed correct because they satisfy the points on the line, or the graph itself of 4x minus 5. Now kindly investigate on this. What if you answered 1 or 4 in the limit of 4x minus 5 as x approaches 2? Let's see what happens.